Welcome to Lecture 3, the Earth's Energy Balance, with more on the greenhouse effect and its enhancement. Here's an outline for this lecture. We will be talking about energy, what it is as it pertains to the atmosphere, to climate change. We'll be discussing solar and infrared radiation. Radiation is a way to transfer energy, and two important types of radiation that you will understand are solar and infrared. Solar radiation comes from the sun. Infrared radiation is what the earth emits. We will be talking about the fate of radiation as it strikes the Earth's atmosphere. The fate of sunlight, for example, as it enters the atmosphere could be absorption, where it's absorbed, taken in. It could be scattered, which means reflected in all directions. Or it could be transmitted, pass through, and then be either absorbed or reflected. We'll be talking about global energy balance, also called the global energy budget. It turns out that as a whole over the globe, there's a balance between incoming energy and outgoing energy. The Earth likes to be in a balance in terms of energy, and if it's taken out of balance, it will attempt to achieve a new balance. And we will be discussing the greenhouse effect in more detail. You'll get a better understanding of the physics of it. Reading for this lecture, Chapter 3 in the Bloom book, pages 54 to 65. We'll be looking at some of the same figures, and I do, to an extent, follow the book. The book will go into more details on some topics. I'll go into more details on others. But it's a really good book, and it's a great reference to have. So that's your reading assignment for this lecture, pages 54 to 65. Here, to start us off, is a figure from the book. This is figure 3.23. And what it shows is albedo, which you'll remember from lecture 2, the fraction of light reflected by an object or surface from various surfaces on Earth. We have albedo on the y-axis, or vertical axis, from 0 to 100%. And we have different surfaces. Now, what are some of the more highly reflective surfaces you see? Well, fresh snow. Fresh snow can have an albedo of upwards of 80%. Older snow has a lower albedo. And why is that? Well, as the snow ages, it tends to turn darker, slightly darker, maybe a gray color. And dirt and material can get in the snow and lower its albedo. There are clouds. Some clouds have higher albedos than others. Cumulus clouds, stratus clouds are both very bright from space, and they reflect a lot of incoming sunlight. Cirrus clouds, which are high clouds, altostratus clouds, which are a form of a middle cloud, they also reflect, but not as much necessarily as the cumulus. Stratus. What about the other extreme? Objects with a low albedo would, of course, absorb much of the incoming sunlight. So, remember we were talking about the dark asphalt parking lot example in the last lecture? You see, asphalt reflects less than 10%, around 5% of incoming sunlight. So it absorbs 95% of the incoming sunlight. Forests are also dark from space. They absorb most of the incoming sunlight. Dark soil or wet soil is low albedo as well. Liquid water has a low albedo. Recall that the oceans are dark from space. But ice cubes, not snow, or ice that's been formed from snow, but ice cubes have a fairly low albedo, believe it or not, perhaps around 35%. That's different, though, from snow, which is lighter in color than a transparent ice cube. Now, we're looking at the albedo for some different surfaces on Earth. Now let's look at albedo displayed over Earth, over the continents. We'll focus on land rather than ocean, because the albedo of the ocean is pretty, it's pretty constant. So, what we're looking at is albedo of Earth's land masses measured by a satellite from NASA called the Terra satellite. And shown are the average values from April 7th, 2002 to April 22nd, 2002. So we're looking at a couple weeks of albedo data from this satellite. We have the satellite in space, and it can measure the albedo of the Earth's land. White areas shown here at Antarctica and northern Greenland, the extreme fringes of northern Canada, show no data. And the oceans are shown in gray, pretty constant albedo. It's low, okay, very low. So, when you look at a figure, you want to understand the legend, you want to understand the scale. We have albedo percentage, and we have a scale from 0 to 50%. Dark purple is very low albedo, close to 0%, hence almost all the sunlight would be absorbed. And then as we get into the blues, the dark blues, followed by the light blues, greens, we're getting into 10 to 20 to 25% albedo. Albedo continues to increase as we go from yellow to orange to red. And by the time we're at dark red, we're talking about 50 or more percent of the incoming sunlight reflected. Now, what does this tell you about the different land masses on Earth? Okay. Where do you see the highest albedos? Look at this figure showing our continents, our large land masses. Where do you see the highest albedos? Well, the northern polar regions. Alaska, northern Canada, Greenland, Iceland. Of course, Iceland just came off that amazing upset, right, of England and the Euro soccer event, which happened after England, also Britain, pulled out of the European Union, Brexit. Kind of an interesting week for them here in late June, early July. Northern Siberia also has a high albedo. And again, this is April, okay? So then let's say someone asks you the question, why is the albedo of these northern polar regions high, okay? Well, think about it. It's April, so that's early spring, okay? It's April 7th to April 22nd, 2002, so that's early spring. Well, what's the land surface like of northern Siberia, northern Canada, Alaska, Greenland, even into early spring, even into early summer? Snow and ice, okay? And remember that snow and ice are very reflective, okay, because they're very light in color, they're very bright, so they reflect almost all the incoming sunlight. So that helps us understand why we have the high albedo in these northern Arctic regions, in these northern polar regions. The Arctic Circle is latitude 66.5 degrees north, and anywhere north of it is considered in the Arctic. Now, we also see high albedos here in this region, in northern Africa. What could cause that? What's takes up a large amount of surface here in northern Africa is the Sahara Desert. And deserts have high albedos, along with snow-covered regions. Okay. So we have our desert. We also have desert area in Saudi Arabia. Okay. The top oil-producing country in the world. Yeah. Now, what about the other extreme? Now, if you want to look for places with very low albedos, you want to look for the purple, the blues. Okay. Can you see any? Okay, we don't have any extremely large bodies of land with albedos of 0 to 10% like we do for albedos of 50+%, but we definitely see some fairly large areas of green, okay, in the 20s in terms of 20, 25, 28% albedo. And if you look closely, you'll see some small areas with blues, okay? Look at some of these areas in South America here. Looked at this area here. See this little patch in Africa. Well, that could be forests. You know, there's forests. There's the Amazon rainforest here in South America, and forests have very low albedos. Okay. Now, what could be happening to albedo over time as a result of climate change? Here are global albedo measurements, so albedo over the entire Earth, from 2000 to 2004. And these are monthly values. So we're looking at the albedo for each month of the year over the entire Earth from 2000 into 2004. Okay, about 5 years of data. The horizontal line, 29.0%, represents the average albedo over the period. Okay, 29%. Oh, that's pretty close to what we said the albedo of Earth was in Lecture 2, 30%. Do you see any trend? Okay. Of course, from month to month, albedo goes up and down. Okay, we clearly see that. We see the monthly variations, the wobbles. But what about the net trend over the 5-year period? If you're going to put a trend line, if you plotted this data in Microsoft Excel and added a trend line to see how the albedo is changing from 2000 to 2004 overall, it would be a decline. Okay, in 2000 to 2001, the albedo was in the area around 29.5%, especially 2000 into early 2001. By the time we get into 2003 into 2004, it's down to more in the range of 28.7, 28.8%. And this shows a decrease, okay? And why? What could cause this? Could be a diminishing snow and ice coverage, okay? We've talked about how the snows at the top of Mount Kilimanjaro are melting away. We've talked about the melting Arctic sea ice in the summertime. Now, yes, this is only 5 years of data. Okay, remember when you talk about climate, you're talking about decades, centuries of data, and you need talk about climate change. You need to be looking at least decades. Yes, this is only 5 years, but this is consistent with what we could expect from climate change, because we can expect the albedo of Earth to decrease as the ice and snow continues to melt. Especially when sea ice melts, the albedo will go from 85 to 90% to around 10%, because the open ocean below the sea ice is the opposite in terms of reflectivity. Unlike the sea ice, which reflects almost all the incoming sunlight, keeps that Arctic region cool, the open ocean below it will absorb almost all the sunlight. And that melting of the sea ice is helping warm that region faster than the rest of the world. Okay, what about energy? What is energy? Okay, we need to understand energy before we can understand how it's transferred and how it relates to the greenhouse effect. How could you define energy? Can you come up with a short, concise definition of energy? The classical definition of energy is the ability to do work or induce change. Okay, it takes energy to do work, right? You need energy when you work. If you work a 9-to-5 job, right? If you don't have energy, you're not going to do work well. Okay, it's going to be harder to. Okay. Perhaps an alternative definition, more relative to climate change, is the following: the capacity to change environmental conditions, for example, temperature of a substance. Now, the example we talked about above, working at a job, that's not quite what the classical definition's talking about. That could help you think about it, but work is, in terms of physics, is force times distance. Okay, so to move against a force requires work, and it takes energy to do that. But in terms of climate change, perhaps, this definition more related to climate change, it's the ability to change environmental conditions, such as the temperature of a substance. So a substance could be a mixture of gases, like Earth's atmosphere, and it takes energy to change the temperature of Earth's atmosphere. And what's happening is the Earth's atmosphere, because of a stronger greenhouse effect, is taking in more energy overall, and that's leading to a higher average surface temperature over time. Okay? When we talk about surface temperature, it's not the temperature of the ground itself. It's usually measured at about 5.5 feet up, about the height of Lil Wayne. And that's what surface temperature is. So it's in the lower part of the atmosphere. Now we know what energy is. How do we transfer it in the atmosphere? There's 3 modes of energy transfer in the atmosphere. And do you know the names of any of them? Pause the video and try to come up with some of the modes, the ways we transfer energy in our atmosphere. One, we have conduction. That's the transfer of energy by collisions between neighboring molecules without any net external motion. So it's a way to transfer energy between a couple objects, basically without any net movement of the objects. Okay, the molecules are touching and bouncing against one another, and that transfers energy. The molecules of the 2 objects, 2 substances perhaps, are making contact with each other and exchanging energy, but there's no net external motion required. Now, this happens in the atmosphere, but it's very inefficient because the atmosphere is a collection of gases, and in a gas, the molecules are greatly spaced, at least much more spaced relative to in a solid or liquid. So conduction does happen in the lowest few inches in the atmosphere, but as a whole, the atmosphere is a fairly poor conductor. Okay, conduction is more important in solid substances, such as associated with heat transfer in soil. But it's important in the lowest few inches of the atmosphere. How the surface transfers heat to the lowest few inches via conduction. We also have convection. Convection. Ever heard of a convection oven? Maybe on one of those 30-minute infomercials. The transfer of energy by mass motions or mass movement within a fluid, water, air, resulting in actual transport of energy. So it's a way to transfer energy within a fluid. It could be a collection of gases, it could be water, okay, it could be another type of liquid, with mass movement. So unlike conduction, which has no net external motion, convection does have mass movement. And the other mode of energy transfer is radiation. Before we get to that, we need to also mention convection happens in both the atmosphere and ocean. For example, turbulence in the atmosphere is a very efficient means of vertical transfer of heat. The term advection applied to the atmosphere or the ocean refers to horizontal convection. So convection can happen vertically, up or down, or horizontally, sideways. And in meteorology, we have a special name for horizontal convection, transferring energy, heat, from one place to another via movement of air, also known as wind. We call it advection. Now, the third mode of energy transfer in our atmosphere is radiation. Radiation. And that is basically the propagation of electromagnetic waves through space. And radiation is very interesting. It's the dominant way energy is transferred between the sun and the earth. And for radiation, what happens is one object emits energy, okay? And another object will then take in that energy, but along the way, okay, as the energy moves from one object, could be the sun, to the other object, the earth, no energy is lost or gained during the movement, okay? Usually all of the energy that's released by one object travels all the way through to the other object, and all of the energy that was released by the one object will then be taken in, released to be absorbed by the other object once it makes contact with it. Here's a nice figure showing how conduction works. We have our candle here, okay? We have our candle. Maybe you use candles in your house, okay? Especially if there's a blackout People might, use candles. Nowadays, maybe they'll use their phones for lights. Candles also can be romantic. And the transfer of heat from molecule to molecule within a substance is conduction. Let's say you're holding one end of a metal straight pin between your fingers and above a candle at the other end of the pin. Because of the energy that they absorb from this flame, the molecules in the pin vibrate faster, okay, than the molecules in your hand initially, okay? And especially the molecules in the pin, we should say, above the flame will vibrate faster, move faster than the molecules on either side of the pin. Well, the faster vibrating molecules above the flame then cause adjoining neighboring molecules to vibrate faster, which in turn pass energy on to their neighboring molecules, and so on down the pin, until the molecules at the finger-held end of the pin begin to vibrate rapidly. And these fast-moving molecules eventually cause the molecules of your finger to vibrate more quickly, which transfers heat from the pin above the flame to your finger and hand. And both the pin and your fingers, where you're holding the pin, feel hot, right? What's going to happen if too much energy is transferred? What's going to happen? You're going to drop the pin because it's too hot, right? We are very thankful for our nervous systems, right? Because if something is too hot, what do we feel? Pain. And usually the hotter it is, the more danger we are in, the more pain we feel. Okay, it's a message to us, right? Let go of that pin before you burn your hand, son. Okay. The transmission of heat from one end of the pin to the other is caused by conduction. Heat transferred via conduction always flows from warmer to colder regions. Heat doesn't flow from colder to warmer regions. It always flows from warmer to colder regions. And generally, the greater the temperature difference, the more rapid the heat transfer. Okay? So the greater the temperature difference over a distance, the faster the heat will be transferred. And when materials, such as the molecules inside the pin, are able to easily pass energy from one molecule to the other, they're called good conductors of heat. Okay. Air is a very poor conductor of heat, which is why most insulating materials have a large number of air spaces trapped within them. Okay? Air is such a poor conductor that even in calm weather, the hot ground will only warm a shallow layer of air, a few centimeters thick by conduction. Okay, a few inches or so. Okay, 1 inch is 2.54 centimeters. So on a hot day, the sunlight comes in, passes through most of the atmosphere, and where does that sunlight get absorbed? Most of it gets absorbed at the surface, and then the ground warms the air above it, but only to maybe an inch or two. Yet air can carry this warm energy rapidly from one place to another, okay, upward, downward. How does this happen? Happens through convection, okay. The transfer of heat by the mass movement of a fluid, such as water or air, is called convection. And this type of heat transfer takes place in liquids and gases because they can move freely. They move faster and more freely than in solids, where in solids the molecules are in kind of a crystalline state. They might be moving, but they're generally moving the same direction. They're tight, they're rigid, close together. It is possible to set up currents of convection in both liquids and gases. Convection will happen naturally in the atmosphere. Here we have our sun. We have a clear day, no clouds in the sky above this land surface. On a warm, sunny day, certain areas of Earth's surface absorb more heat from the sun than others. As a result, the air near the Earth's surface is heated somewhat unevenly. Okay, certain parts of the surface have lower albedos than others, or maybe darker than others, and the rate at which the surface warms up, the ground warms up, it's not just a function of albedo, that's very important, but also what it's made of. Okay, if soil has high moisture content, then some of the energy that would normally go into heating the soil up, okay, will instead go to evaporate the water, and so the soil won't heat up as fast. But if you have drier soil, it'll heat up faster than wet soil. Anyhow, some parts of the surface become warmer than others. You have this, so at 2 p.m. here, you have this warm bubble of air. Okay, you have this warm bubble of air above the warmer surface. Now, air molecules adjacent to the hot surface bounce against them, thereby gaining energy by conduction. This heated air, warmer air pocket, is buoyed upward and rises. Okay, and it will continue rising over time. So here's 15 minutes later, and it's rising upward. So what's happening is warmer air from the lower atmosphere is being transferred upward. Okay, large bubbles of warm air called thermals transfer heat upward. Cooler, heavier air flows toward the surface to replace the rising air. Okay, nature doesn't like vacuums. You can't just have air constantly rising upward and leaving. There has to be air to come back to replace it. What happens is cool, dense air sinks and replaces that warmer air that left. The cooler air becomes heated in turn, rises, and the cycle is repeated. Here's a nature example of the significance of convection. The sport of paragliding is dependent on thermals. Okay. You see this person here paragliding. Well, they need those rising currents of air to get upward, right? To move upward. Okay. And also some birds are weather savvy. Hawks, for example, seek out rising thermals and ride them up into the air as they can scan the landscape for prey by doing so. And this helps the birds conserve a great deal of energy because they don't have to flap their wings as they circle higher and higher inside the rising air current. Okay, saves them energy, right? They don't have to flap their wings as much to go upward because they can ride the rising thermal. So, electromagnetic radiation is the main way energy is transferred between the sun and Earth. And the interaction between this electromagnetic radiation, gases in Earth's atmosphere, is the basis of the so-called greenhouse effect. Therefore, an exposition on electromagnetic radiation is necessary before embarking on an explanation of the greenhouse effect. Okay? We need to understand the electromagnetic radiation, what it is, how it works, in order to understand the greenhouse effect. Okay? Here's a question for you before we go into more detail about electromagnetic radiation. How long does it take sunlight to reach Earth? Okay? Any ideas? How long does it take for the sunlight, 93 million miles away, the light emitted from the sun 93 million miles away, to reach our planet? It takes about 8 minutes, slightly more than 8 minutes. 8 minutos. Okay? Now, electromagnetic radiation is made up of waves. Nearly all of the energy impinging on Earth from space is electromagnetic radiation. And electromagnetic radiation has a split personality. It exhibits properties of a particle, reflection, okay, but also of a wave, such as diffraction, the bending of radiation around small objects, and refraction, the bending of radiation as it passes through different materials with different densities. So we consider electromagnetic radiation to be composed of particle waves, okay? Both particles and waves, okay? It travels in these waves with particles riding along the waves. Radiation is the transfer of energy by particle waves. All particles are also called photons. You may have heard of this term, which means packets of energy. So you have waves traveling for electromagnetic radiation. Inside these waves, you have these packets of energy. Okay. The most important general characteristic of radiation is wavelength, which is given by the Greek letter lambda. And how wavelength is defined is shown in the figure above. Okay? What you can see is that it's defined as the crest-to-crest distance, or ridge-to-ridge distance. It's the distance from one crest of the wave to the other. It's the same distance as between the two troughs of the wave, okay, the dips of the wave, if you will. And the reason that's the most important general characteristic is because it allows one to differentiate between types of radiation, okay? If you want to know what type of radiation you're dealing with, we'll be talking about the types of radiation in the coming slides. You need to know the wavelength of radiation. Now, radiation travels through space at the speed of light in a vacuum. Light is actually one form of radiation. Okay, visible light is one type of radiation. And all radiation, not just visible light, but other types of radiation as well, travel at the same speed, which is the speed of light in a vacuum. Not the floor cleaner, but empty space. And that value is 3 times 10 to the 8th meters per second, or for us Americans, 186,000 miles per second. Yes, that is extremely fast, right? How fast have you ever driven? Okay, hopefully not too fast above the speed limit. Well, in 1 second, light or other types of radiation that travel through space will move 186,000 miles. Okay, just for reference, the moon is about 200,000 miles away from Earth, so the image you see of the moon is about a second old. Okay, it takes light from the moon, that's actually reflected by the moon from the sun, a little over a second to reach Earth. The moon, we'll be talking about what affects how much radiation, the type of radiation objects emit. The moon's not hot enough to emit its own light, but it reflects light from the sun to Earth, and that light takes a little over a second from the moon to reach Earth. Now, the sun is 93 million miles away from Earth on average. So it takes, if you do the math, it's about a little over 8 minutes. So the sun you see is 8 minutes old. Okay, if you're high on a mountain, okay, if you've ever done hiking or camping and you're high up on the mountain watching the sunrise, it's a very beautiful sight. When the sun rises over the horizon, or this could be over the ocean, okay, that's about that means that the sun actually really rose 8 minutes before, okay, and it's a little different also because of refraction, but it's pretty close to that. Sound travels at a much lower rate than light. The speed of sound near the Earth's surface does vary with respect to temperature and humidity, but has an average value of about 760 miles per hour. Okay. Now here's a nice summary figure for the 3 types of energy transfer in the atmosphere. This time, here's your hand. You're holding this pot of water over a fire. The fire is hot. It's emitting radiation upward, which travels in the form of waves, as you can see. Now, the water in the pot is not all the same temperature. Of course, the water in the bottom of the pot is closer to the fire, so it heats up first, faster. And then what happens is those heated molecules in the bottom will transfer energy via mass motions, okay, within the water upward, and that's convection, okay. In the heated pot of water, the molecules in the heated pot will then transfer energy to the neighboring molecules, which transfer energy to the neighboring molecules, and so on until your hand gets hot, right? That's conduction, transfer of energy via neighboring molecules without any net external motion. There's a reason we have pot holders, right? Now, let's focus more on radiation, because again, we need to understand radiation in order to understand the greenhouse effect. I have a question for you. What emits radiation? Okay? What emits radiation? What do you think? Does everything emit radiation? Well, all objects with a temperature greater than 0 Kelvin, or absolute zero, minus 273.15 degrees Celsius, emit some type of radiation. Okay? Remember, at absolute zero, that's the lowest theoretical possible temperature, molecular motion stops. Remember how we define temperature? The average speed of the molecules? And the lower the temperature, the slower the molecules move until you reach 0 Kelvin, where they're no longer moving. As long as the molecules of an object are moving, it will emit some form of radiation. Okay? So what are some examples can you think of objects that emit radiation? You're emitting radiation right now. Okay? You know, there might be somewhat of a negative connotation with the word radiation, right? Maybe what comes to mind when you think of radiation is harmful nuclear radiation, which can cause cancer. Okay, radiation poisoning, you might think of that. In science, radiation is energy transferred via electromagnetic waves, the propagation of them. And everything with a temperature greater than minus 273.15 Celsius is going to emit radiation. Okay, the type of radiation given by the wavelength and the amount of radiation emitted by an object depends on temperature, but every object with a temperature greater than 0 Kelvin emits radiation. So that includes the sun, which is hot, and the earth. Now, there are two extremely important radiation laws that you need to understand. Okay. 1. Warmer objects emit more intensely than colder objects. This is known as the Stefan-Boltzmann law. The warmer an object is, okay, the higher the temperature, the faster the molecules move on average. Basically, the more radiation it emits. Okay. And if you look at your book, you can find the actual formula. It turns out the radiation emitted by an object is proportional to the fourth power of temperature. Okay. The second important radiation law to know is that warmer objects emit a higher proportion or greater percentage, greater fraction of their total energy at short wavelengths compared to colder objects. This is known as Wien's law. So the warmer an object is, the larger proportion of its energy it emits will be at shorter wavelengths. And in general, the warmer an object, the shorter the wavelength of peak emission. Okay? Now, objects don't emit only at one wavelength. They can emit over a variety of wavelengths. But the warmer an object is, the lower, in general, the shorter its average wavelength. Now let's talk about some types of radiation. Okay? And remember, the characteristic that helps differentiate types of radiation is wavelength, lambda, distance between the crests of the wave. Here we have 7 types of radiation. Okay, maybe you're seeing some of these and they're ringing bells. That's the leftmost column. Then we have relative wavelength, shown by these figures showing the waves. We have typical wavelength value in meters. And for reference, 1 meter is about 3.3 feet. And in our final column on the right, we have energy carried per wave or photon. And we generally think of electromagnetic radiation as particle waves. Okay, so we have these waves moving, and they're carrying photons or particles of energy along them. So, let's check out our types of radiation. We have AM radio waves. Okay. A radio station on the AM dial will emit energy, okay, that is then picked up by the receiver, okay? And typically, the wavelength of a AM radio wave is about 100 meters, a little more than a football field, okay? So if you're listening to an AM station, if you're in the Bay Area, 740 for all news, 680 if you're a Giants fan for the games, okay? waves that travel from the transmitter of the station to your receiver have a crest-to-crest distance of about 100 meters. We also have television waves here. Of course, nowadays, most people have cable, or they watch their shows on the internet. Okay, a few people, nowadays actually still have analog TVs, right? Or they could digital TVs, but without cable, right? They still use over-the-air signal, and those TV waves have a wavelength of about 1 meter. Okay, so 1/100th of the wavelength of the radio wave. So what do you see? Shorter wavelength. So you see a shorter crest-to-crest distance. Microwaves are shorter still. So what's happening as you're going down this list of the different types of radiation? The wavelength is decreasing. And as the wavelength decreases, what happens to the energy carried along the wave? It increases. So the shorter the wavelength, the more energy carried along the wave. And this should make sense to you because the shorter the wavelength, the warmer, that generally means the warmer the object, right? And the warmer the object, the more radiation emitted. So this should hopefully make sense to you. Microwaves have a typical wavelength of 10 to the minus 3 or 1,000th of a meter. What do we call 1,000th of a meter? Millimeter, right? Infrared waves are what the Earth emits, and they have a wavelength of about 10 to the minus 6 or 1 millionth of a meter, also known as a micrometer. Visible light has a typical wavelength of 5 times 10 to the minus 7th meter, or 0.5 micrometers. But it varies. Different colors have different wavelengths. At one end of the spectrum, we have purple or violet with a wavelength of about 0.3 micrometers. And then at the other end of the spectrum, the longest wavelength of light is red with a wavelength of about 0.7 micrometers. Oh, look at this. If you're at the end of the visible light spectrum here, around 0.7 or so micrometers, and then you go a little long, the wavelength becomes a little longer, you switch from visible light to infrared. It's called infrared for a reason. Also, if you're at the shortest wavelength of visible light, which is violet, near 0.3 micrometers, and your wavelength becomes a little shorter and you're no longer light, the type of radiation being carried is ultraviolet. Okay, help you remember. Ultraviolet has a typical wavelength of just 0.1 micrometers. Okay, and these waves are invisible. Okay, there's energy being carried, but we can't see radiation. Okay, and then we have X-rays, and they carry a lot of energy. X-rays have a typical wavelength of 1 billionth of a meter. Okay, very short wavelength, very powerful. That's why X-rays are so powerful they can see inside. The X-ray machines can see inside the body, right? If you're checking to see if you have a broken bone, you might get an X-ray. Okay. Now let's focus more on solar radiation, the radiation outputted by the sun. So we would like to ask and answer the question, what type of radiation does the sun emit? Okay, of course the most familiar type of radiation is the light that the sun emits, right? But if we consider the energy output from the sun as sunlight, that radiation is not just visible light. Okay, there's other forms of radiation that the sun emits. And here on this figure, what we're looking at are different types of radiation that the sun emits. Okay, remember on the last slide we were talking about the types of radiation, the relative and typical wavelengths, and the energy carried along the waves for each type. And so not only can we see the types of radiation that the sun emits, ultraviolet, visible light, which humans can see with the eyes, near infrared, far infrared, microwaves, TV waves, and even radio waves. But you can see the relative percentages of the sun's total radiation that is composed of a certain type of radiation. Okay, so you start to understand where does the sun emit the majority of its radiation. Okay, where does the sun not emit much radiation? So you'll remember from the last slide that the shortest wavelength of radiation we were talking about were X-rays. And the sun really doesn't emit any X-rays, okay? It's not hot enough to. Remember, the hotter an object, the greater proportion of its radiation at shorter wavelengths. But the sun does emit ultraviolet radiation, okay? Ultraviolet radiation, and we'll remember from talking about it in Lecture 1 that ultraviolet or UV radiation can cause sunburn, skin cancer. Thankfully, the ozone layer protects us from most of it before it reaches the surface. So if you go to shorter than about 0.4 micrometers, okay, so this Greek letter mu here means micro, and 1 micrometer being a millionth of a meter, very short wavelength. The radiation that the sun emits that's shorter than 0.4 micrometers is generally ultraviolet. And 7% here of all solar radiation is ultraviolet. So 1/14, okay, of the sun's radiation is ultraviolet. And that might not sound like a lot, but remember the sun, it's very hot, as you probably already know. We talk about the temperature. It's very hot, and the sun emits a lot of radiation, as you probably understand. Okay, the sun emits a lot of radiation, so that's 7% of a lot of radiation. And if it wasn't for the ozone layer, we'd have a lot more issues with skin cancer and sunburns. Okay, not just tans. Okay, and then you see visible light. Again, violet, purple represent the colors with the shortest wavelengths of visible light, whereas oranges and reds are the colors with the longest wavelengths of visible light. And the wavelengths of visible light go from about 0.4, maybe closer to 0.3 to 0.7 micrometers. Okay, and close to half, not quite half, but close to half of all solar radiation is visible light. Okay, 44% of incoming solar radiation is visible light. And of course, this is what brightens the day, okay? And we understand the importance of the visible light after the sun dips below the horizon, because of course it's dark, okay? And then you see near infrared. So near infrared radiation has a wavelength between 0.7 micrometers and 1.5 micrometers. And it's called near infrared because it's near visible light. Okay, so it's infrared. These wavelengths of radiation are longer than for visible light, and humans can't see them, although some certain organisms can actually pick up and detect infrared light. But these are near visible, okay, as opposed to far infrared, longer than 1.5 micrometer, which are further. Okay, they're farther from visible light. And 37%, a little over a third, of the solar radiation is near infrared, from 0.7 micrometers to 1.5 micrometers. So, one thing that you also see here is that the sunlight's peak radiation intensities per wavelength are in the visible spectrum. Look at the y-axis, the vertical axis of this diagram. It shows radiation intensity, or basically amount. And for this entire curve, where do you see the greatest radiation intensity or amount? It's at this point here, which is in the somewhat in the middle of the visible spectrum. It turns out it's at 0.5 micrometers. 0.5 micrometers, 1/8 of a micrometer, is the wavelength of maximum emission for the sun. So basically, if you look at all wavelengths of solar radiation, okay, all the types of radiation the sun emits, where you're going to find the greatest amount emitted total, it's at about 0.5 micrometers. And that is in the visible spectrum, okay? But again, Sunlight's made up of other forms of radiation. It's mainly made up of the following: visible light, 44%, or nearly half. Infrared radiation, if you add up near infrared, 37%, and far infrared, 11%, you get 48%. So 48%, also close to half of all solar radiation, is near infrared. It's very interesting because if you look at those alone, that's visible light and infrared radiation. Well, those two forms of radiation make up 92% of all solar radiation. Okay, but the 7% of the solar radiation, or energy, if you want to think of the output from the sun as energy, you can. 7% is ultraviolet. So what's left, if you add 44 plus 48 plus 7%, you're left with about 1% or so. And that's where we have these longer wavelengths of radiation. The microwaves, okay? The TV waves, and even radio waves, okay? So it's possible to pick up static from the sun, okay? But it's very little, extremely little of the solar radiation is actually a form of radio waves and TV waves, okay? So we had mentioned how the sun is very hot. Turns out the sun's average surface temperature is a staggering 6,000 Kelvin, or 10,340 degrees Fahrenheit. That's the sun's average surface temperature, over 10,000 degrees Fahrenheit. Okay, it's very hot, and so we're going to see that's why, because of it's much hotter than Earth, it emits primarily shorter wavelengths. Okay, we're going to see that. And we're going to look, now we have a good understanding of solar radiation, what it's composed of. Okay, visible light, infrared, ultraviolet. But keep in mind, focus, that the peak intensity of solar radiation, where are you going to find the wavelengths with the maximum amount of radiation emitted? Okay, it's in the range, it's in the visible light spectrum, the range of visible light. It's different from the Earth and other planets. So now let's talk about terrestrial, also called long-wave radiation. Okay, planets mainly emit infrared radiation. Okay, whereas the sun emits, as you see, the sun emits visible and infrared. Okay, it's just a little more, slightly more infrared than visible. But even though that's true, you also have to remember that the maximum emission intensity or amount is in the visible spectrum. Okay, so that's where you're going to find the peak amounts of radiation emitted per wavelength are in the visible spectrum. That's different from planets. Okay, planets mainly emit infrared radiation. Okay, maybe a little bit of visible light, a tiny bit of ultraviolet, if any. Mainly, though, infrared, and that's, for planets, you're going to find the peak wavelengths of emission in the infrared spectrum. So, what do you think? Does radiation emitted by planets occur mainly at wavelengths longer or shorter than those contained in solar radiation? Let's think about this. Does radiation emitted by planets such as Earth, such as Venus, we were of course discussing Venus and its atmosphere in the last lecture, Mars, and even colder planets like Pluto, would you find the radiation emitted by the planets mainly at wavelengths longer or shorter than those contained in solar radiation? The answer is, what did you come up with? It's longer. Why? How can you explain this? Well, remember the Stefan-Boltzmann law, okay? Or, Wien's law. Wien's law basically says that warmer objects emit a higher proportion of their radiation at shorter wavelengths than cooler objects. And it says, it basically says that warmer objects, the warmer an object, the shorter the wavelength of peak emission. Okay? Now, the sun is much warmer than planets, and so it's going to have a shorter wavelength of peak emission. Whereas planets are cooler than the sun, So they emit mainly at wavelengths longer than what you find from in the radiation from the sun. Okay, so we often call solar radiation shortwave radiation. Shortwave radiation is the same basically as radiation from the sun. Okay, so anytime you hear shortwave radiation, that's referring to the radiation from the sun or solar radiation. Whereas planets emit in all directions terrestrial radiation or long-wave radiation, okay, because it's the radiation's at longer wavelengths than the solar radiation, and it's also infrared radiation, okay. So infrared, terrestrial, or which means planetary, long-wave, those three terms, infrared, terrestrial, long-wave, are basically interchangeable, okay. And solar and shortwave are also interchangeable when you're discussing radiation. Okay, so understand the difference in the wavelengths between solar radiation and terrestrial radiation. And we can use Wien's law to help us understand why the wavelengths of the types of radiation are different. Now, we can also talk about the Stefan-Boltzmann law and relate it to the difference in radiation between the sun and planets. Okay, so the sun is much hotter than planets. Okay, remember that the sun's average surface temperature is 10,340 degrees Fahrenheit. And by the way, it gets even hotter as you go deeper in the sun. Okay, it can get to tens of thousands of degrees Fahrenheit if you start to descend into the sun. Okay, but the average surface temperature is slightly more than 10,000 degrees Fahrenheit. And that's hotter than any of the 8 or 9 planets, right? Depending on what year it is and whether you consider Pluto a planet or not, right? Still. Even Venus, which of course is staggering hot, remember Venus's average surface temperature is 896 degrees Fahrenheit. Well, that's nothing compared to 10,000 degrees Fahrenheit, right? So because the sun is much hotter than planets, solar radiation consists primarily of shorter wavelengths than terrestrial radiation. Okay, this is consistent with Wien's law. But now we can also talk about the Stefan-Boltzmann law, okay, in a minute. So first, if we can compare solar radiation and Earth's radiation, what do we see? Well, we see that the maximum wavelength of emission for solar radiation is 0.5 micrometers, as was said. Sun emits shortwave radiation. Whereas the Earth's peak wavelength of emission is 10 micrometers. Okay. So if you're going to ask, oh, well, at what wavelength, would I find the greatest amount of radiation emitted by the Earth? It's at 10 micrometers, which is in the infrared spectrum. Okay. And the Earth has an average surface temperature of 288 Kelvin, or if you do the conversion, 15 Celsius, 59 degrees Fahrenheit, and rising, right? And the majority of Earth's radiation is in between about 5 micrometers and 20 micrometers, okay? And so very little, if any, radiation is emitted from the Earth in the form of visible, right, between 0.4 and 0.7 micrometers. But then now we come to the Stefan-Boltzmann law that says the warmer an object, the more radiation it emits, okay? That's what it means. And what do you see? If you have radiation intensity or amount per wavelength, right? You look at your certain wavelength, and then you look at where the line or the curve is, and that tells you the radiation intensity or amount for that wavelength. What if you wanted to get total radiation emitted over all wavelengths? Okay, how would you find it? You take the area under this curve. Okay, if any of you have taken calculus, you'll remember that the integral is the area under the curve. And basically, if you integrate over all wavelengths, you add up the area under all wavelengths, you'll get how much radiation is emitted in total. And what you see is that it's a lot more for the sun than the Earth. Okay, compare this area under this curve for Earth, compare it to the sun. And also, another thing that needs to be mentioned is that this y-axis or vertical axis, when you comparing the sun and the Earth, it's not really linear. Okay, so it's actually even a lot more greater in difference between the total radiation emitted by the sun and Earth. As was mentioned earlier, the amount of radiation emitted by an object or surface is proportional to the fourth power of temperature. Okay? And so, because the sun is so much hotter than the Earth, and radiation emitted or output or given off, okay, that's another word for emitted, by the sun by an object is the proportion of the fourth power of temperature. The sun emits an extremely significantly more amount of radiation than the Earth. Okay, let's have some review questions, because we've been talking about these two laws. We've been talking about a lot of types of radiation. We're definitely covering a lot of material, and want to check up and see how we're doing. Considering our previous discussion, which object would emit higher intensity radiation, Earth or Sun? Well, the answer is Sun, because it's much hotter. Therefore, according to the Stefan-Boltzmann law, it emits more radiation. Okay, we saw that also in the previous slide, in that figure on the right. Second question. If you were examining the radiation emitted by both the Earth and the Sun, okay, which would have a longer wavelength? So we're not asking which of these two objects or bodies emits more radiation. We're asking if you're looking at the radiation from Earth, okay, and the Sun, which would have a longer wavelength? Well, the answer is Earth, because according to Wien's law, warmer objects emit at shorter wavelengths. That's what it means basically if you break it down, whereas the cooler objects emit at longer wavelengths. And since Earth is cooler than the Sun, right? The Sun's not cooler than the Earth's a lot cooler than the Sun, its radiation is at longer wavelengths, as we saw on the previous figure. And here's another question for you. Okay, we're talking about the Sun's radiation, also called solar radiation. We're talking about Earth's radiation, also called infrared or long-wave radiation. Well, what type of radiation are you emitting right now? Okay, what type of radiation are you emitting right now? Well, infrared. Okay, you are all emitting infrared radiation right now. Okay, then how come, when you look at somebody, you see colors, right? You see their skin color, their hair color. Are they emitting visible light? Well, to answer that question, think about if they were put in a room and the artificial lights were turned off, and if it was daytime, the windows are covered. Would you be able to see them? Okay? Can we see each other in the dark? We can't. Okay? And why can't we emit visible light? Well, we're not hot enough. Okay? And if that offends you, okay, we're not hot enough to emit visible light, then you can think of it as, oh, we're too cool to emit visible light. Okay? Get it? All right. So we're too cool to emit visible light. We emit infrared radiation. Okay? And some cameras, though, can actually pick up on infrared radiation. Okay? So what we have here is a person. This is you, right? Here you are. Walking through the woods on a cold night. Okay? So you can pick out the trees. And what the colors represent are basically infrared radiation emitted or given off by different sources, trees and you. And the thing is, it's a cold winter night, so the trees and also the air is colder than you. Okay, I don't think the camera can pick up on the radiation emitted by all the molecules between the camera and the trees. Okay, it's emitting radiation emitted. It's detecting radiation emitted by solid objects. Okay, but the trees on a cold winter night are lower in temperature than you. So you are in these bright yellow and red colors, as opposed to the trees and the woods in purple and blue. Okay, because you're at a higher temperature, you emit more radiation, and in the photograph, those higher temperatures correspond to these colors. Okay, and it also looks like you're hotter in your center. Okay, and that perhaps makes that sense, because what's the source of body heat? It's the heart, isn't it? Now, obviously the sun provides the earth with its energy. Okay, again, the sun is the source of energy on earth. Okay, the question is, how much of the sun's energy does the earth actually get? Okay, And you'll remember from lecture 2 that Earth's average albedo is about 30%. So of all sunlight that strikes the planet, and when we consider the planet, we're not just including the solid surface, but we're also including the atmosphere and their gases and clouds and aerosols. You'll learn more about that term soon. But what about if we were going to ask, how much is actually taken in by the surface? Okay, because the sunlight might not get reflected before it even arrives at the surface. So we have to understand what happens to the sun's energy, okay, as it is intercepted by Earth. And there's 3 general fates of the sun's energy. Okay, can you think of any? Okay, what's one that we've been talking about? Reflection. And scattering is reflection in all directions. Okay, so so this is one. Okay, it could be scattered or reflected in all directions, or it could be reflected in one direction. Okay. Now, if it's not reflected at the surface, okay, what's going to happen if sunlight's not reflected, but actually not reflected? It will be taken in or absorbed by the surface. So you have the sun's energy can be scattered, reflected away, or it can be absorbed. But there's a third fate of sunlight as it enters the top of the atmosphere before it gets to Earth. Can you think of it? Can you come up with it? Begins with a T. Transmitted. Okay? So what transmitted means is that when the energy is transmitted, it passes through. Okay? So, of course, the sunlight can pass through the atmosphere and then be scattered or absorbed at the surface. Okay? Let's talk in more detail about what on Earth and in its atmosphere can scatter, absorb, and transmit. Okay, let's talk about more detail for these terms. Here's what when scattering happens. Well, it happens when solar radiation is reflected by what? What in the atmosphere can reflect sunlight? Okay, what in the atmosphere can reflect sunlight? And when I say sunlight, I'm not just talking about the visible light, but I'm talking about the other forms of radiation from the sun too, the near infrared and the ultraviolet. But I'll try during the semester generally more say solar radiation or shortwave radiation, just because I feel like if someone hears sunlight, they automatically assume visible light. Okay. Well, there's a few things in the atmosphere that can reflect solar radiation. Gases, okay? Nitrogen and oxygen are the 2 most abundant gases in our atmosphere. Carbon dioxide is an important greenhouse gas that's risen dramatically in concentration in the last 150 years. And now we're going to learn more about how much of the solar radiation is reflected by the atmosphere, but it's fairly little, okay? Most of the radiation is actually makes it solar radiation, that is, makes it through the atmosphere. At least when it encounters gases, okay? Aerosols are microscopic solid or liquid particles suspended in the atmosphere. They're microscopic, very small in size, okay? So microscopic means particles, either solid or liquid in the atmosphere. Can you think of any? There's 3 main examples of them, and we'll talk about them in more detail throughout the semester. There's dust, okay? We're used to dust, it builds up in the house if we don't vacuum or, sweep, right? There's salt, which can come from the ocean. And then there's smoke, okay? Come from fires, volcanic eruptions, right? Well, we also have clouds. Clouds can reflect sunlight, okay? You might have noticed on a cloudy day, it could be cooler than on a clear day, okay? Because the clouds reflect the sunlight, okay? Then we have the Earth's surface, okay? What makes it down through the atmosphere, through the gases, through the clouds, okay, through the aerosols, can then be reflected at the surface, okay? Now remember, albedo is the fraction of light reflected by an object or surface, And we were talking on the first or second slide of the lecture about the albedos of different surfaces on Earth, right? Remember? And we said how snow, especially fresh snow, is very reflective, right? Whereas dark asphalt is very absorbent. Okay. Speaking of absorption, where can that happen, or how can that happen for Earth? Okay. What about the atmosphere? Well, the gases in the atmosphere can absorb solar radiation or energy from the sun, and clouds can also absorb solar radiation. Okay. Some clouds are better at absorbing than reflecting. Okay. We'll talk, and it can depend on the cloud cover or the cloud color. It can depend on the cloud thickness, what the cloud is composed of. Okay, clouds can be composed of liquid droplets and ice crystals, and it can happen at the surface. Okay, so some surfaces like the dark asphalt parking lots, the open ocean, the forests absorb the majority of sunlight that strikes them. And then we have transmittance, okay? We're passing through. That happens generally when solar radiation passes through the atmosphere to the surface where it will be absorbed or reflected, okay? And the ground and solid earth is not very good, not a very transmissive medium for solar radiation, okay? In general, once the solar radiation makes it to the surface, okay, it's going to be either taken in and used to heat the surface up, or reflected, bounce off back into the atmosphere and then back into space, okay? The ground is not very transmissive, okay? Of course, if you go underground or you go in in the ocean, it gets very dark, and the ground being a solid, unlike the atmosphere, a mixture of gases mostly, it's hard for the radiation, including the visible light and near infrared, to penetrate very deep in the ground. Okay, so transmittance happens in the atmosphere, but not so much in the solid Earth. Okay, and here's a nice figure illustrating the fate of solar radiation when it strikes an object, figure 3.31 in the book. Again, you're noticing I'm using some of the figures from the book. And this is a nice figure because it shows incident, or basically net initial radiation from the sun coming in. And here's an object, okay? And we see the radiation at a short wavelength. And it could be absorbed, and then it gets taken in and used to heat up the object, okay? And then the object can heat up and emit radiation at longer wavelengths, perhaps, because it's cooler than the sun. It can be reflected, bounce straight off at the same angle it came in, okay? And then some certain materials can reflect in all directions, such as atmospheric gases, okay, and pollution particles. And then some of the radiation, incident radiation, is not taken in, absorbed, not reflected, but it passes through. It transmits. And by the way, have you heard of refraction? That's the bending of light as it enters a denser or less dense medium. Okay? When light from the sun goes from empty space, where there's basically, no air molecules, to a denser atmosphere where there's a lot more molecules per volume, okay, and hence mass per volume, that's what density is, it bends, okay? Refraction is the bending of light, okay? Or other forms of radiation as it passes through a denser or less dense medium. And we're familiar with this. You may recall that liquid water, it's about 3 times, it's actually 1,000 times, but I meant 10 to the 3, okay, by a factor of 10, 3 times the power of 10, that's what I meant. 1,000 times more dense liquid water is than atmosphere, okay? And so if you ever are in a bathtub or a pool and you look down and go in and look in the water and try to see your feet, they might appear distorted, okay? And maybe your legs will as too, okay? Because the light's getting bent, okay? Absorption of radiation. Absorption of shortwave radiation or solar radiation by atmospheric gas molecules is fairly weak. Okay, So it turns out that the atmosphere is generally transparent to solar radiation. Most absorption of shortwave radiation occurs at the Earth's surface. And the reason I say the atmosphere is generally transparent to solar radiation is because not much solar radiation is absorbed in the atmosphere, and not a whole lot is reflected, okay? Especially true for atmospheric gases. So radiation from the sun that passes through the gases in our atmosphere is generally not going to be absorbed, it's not going to be reflected, so it passes through. And a majority of the absorption of the shortwave radiation that happens for Earth takes place at the surface, not in the atmosphere. And most atmospheric gases do not interact strongly with long-wave radiation. So most of the gases in the atmosphere, including the two that make up 99% of the atmosphere by volume, just talking about dry air, not including water vapor. But if you're including water vapor, it's still an extremely high percentage. It's around, 99%. Okay, nitrogen and oxygen make up 99% of dry air by volume. They don't interact strongly with long-wave radiation. And long-wave radiation is what the Earth emits. Okay, it's outgoing radiation from Earth's surface. But there are special types of gases that do interact strongly with long-wave radiation. They are called the greenhouse gases. So the molecules that make up greenhouse gases are able to absorb certain wavelengths of Earth's emitted long-wave radiation. Okay, and the long-wave radiation that's released by Earth is in the form of infrared. And so these certain greenhouse gas molecules, such as carbon dioxide, methane, nitrous oxide, are special because they are able to let in the shortwave radiation, okay? They're pretty transparent to the incoming solar radiation. But what they can do is absorb and trap certain wavelengths of Earth's outgoing radiation, and that contributes to the greenhouse effect. And the stronger the greenhouse effect, the warmer the surface, generally, all else being equal. This figure shows absorption of radiation by gases in the atmosphere. Now there's a lot of parts to this figure. The top 5 parts show the percentage of radiation that's absorbed at a certain wavelength for a specific gas in the atmosphere. The third part down, it actually includes both oxygen and ozone. So if you have 2 oxygen atoms combined, you have diatomic oxygen, which makes up 21% of dry air by volume. And if you have 3 oxygen atoms combined, as you'll remember from earlier discussion, that means you have ozone, okay? So, what is really valuable about this figure is that it lets us look at a certain wavelength of radiation. Could be ultraviolet here, shorter than about 0.4 micrometers. It could be visible between 0.4 and 0.7 micrometers. It could be infrared between 0.7 and 20 micrometers. And it looks at, for that wavelength of radiation, does a certain gas absorb well, okay, or does it not absorb well? It gives you the figure gives you the percentage of radiation at a certain wavelength that's absorbed by a certain gas. And the last part of the figure here shows percentage of absorption of radiation for these different wavelengths by the total atmosphere. So that includes all the gases in the atmosphere. Okay, nitrogen, oxygen, the 2 most abundant, argon, and the other trace greenhouse gases, which are so important in the atmosphere, such as methane, nitrous oxide, carbon dioxide, the most abundant anthropogenic greenhouse gas, and water vapor is a greenhouse gas as well, a natural greenhouse gas. Now, if you take a look at water vapor and carbon dioxide, you'll notice that there's many different wavelengths in the infrared spectrum where they absorb well. So for water vapor and carbon dioxide, they are able to absorb many different wavelengths of Earth's outgoing infrared radiation. Okay, you'll remember that the Earth emits most of its radiation between about 5 and 20 micrometers. So, and if we look at 5 and 20 micrometers, we see these peaks where all the radiation emitted at that wavelength by our surface of the planet, or by the surface of our planet, I should say, is absorbed. Okay, so here in this region, between perhaps 5 and 0.7 micrometers, and then water vapor absorbs well greater than about 0.15 micrometers, and it even is able to absorb a significant portion of radiation between 12 and 15 micrometers. Okay, and then you see some of these peaks for carbon dioxide. Notice that both water vapor and carbon dioxide, however, do not absorb at all in the visible spectrum. So the purple shading is showing absorption percentage, but notice how you don't see any purple shading or any of these peaks for water vapor and carbon dioxide here in the visible spectrum. Why is that? Because they don't absorb visible light. So recognize that water vapor and carbon dioxide, along with the other greenhouse gases, methane, nitrous oxide, have this ability to let in the visible light from the sun, and also let in ultraviolet. Okay, and yet they're able to let in the visible light from the sun, and they're also able to let in the near infrared radiation from the sun. Okay, all these greenhouse gases are, and that's most of the sun's radiation, right? Remember, the overwhelming majority of solar radiation is ultraviolet, visible, and near infrared. Okay, very little in the higher, longer wavelengths. So they let it in, but what can they do? They can absorb certain wavelengths of Earth's outgoing infrared or long wave radiation. Okay, and certain different greenhouse gases are able to absorb different parts or different wavelengths of Earth's infrared radiation. So if you put all the gases together as a whole, what do you see? That with the exception of the atmospheric window here, between about 8 to 11 micrometers, with the exception right around 10 micrometers, where there's a gap, okay, in absorption, Earth's outgoing infrared radiation between 5 and 20 micrometers gets absorbed, okay? But if you add up the effects of nitrous oxide, methane, ozone, okay, of course ozone is able to absorb the ultraviolet radiation from the sun before it gets here. So this is very important, okay? And by the way, clouds can even absorb wavelengths of radiation between 8 and 11 micrometers, which are otherwise passed up by the greenhouse gases. So clouds have the effect of closing this atmospheric window. Now, you'll remember the title of the lecture was Earth's Energy Balance, right? And we talk about that because we're dealing with the incoming and outgoing energy being balanced, okay? Being balanced. So, this can be thought of as the conservation of energy, okay? And now it turns out that the energy balance applies to a few different regions. One, the top of the atmosphere. The energy entering the top of the atmosphere equals the energy leaving the top of the atmosphere, okay? What comes in must go out, okay? What goes out must be balanced by what's coming in, okay? We're not saying necessarily it's the same type of radiation. So that statement, it needs to be modified a little, right? We're not saying that everything that comes in is going out at the top of the atmosphere, but what we are saying is that what is coming in is balanced by the amount going out. It might be different types of energy and radiation, but the total amount coming in, entering the top of the atmosphere, equals the energy leaving the top of the atmosphere. Now also, the energy gained by the atmosphere equals the energy lost by the atmosphere. Now the atmosphere is thin, it's very thin, okay? If Earth was the size of a billiard ball, the atmosphere would be like a tiny coating of dust, okay? So it's very thin, and yet it's definitely three-dimensional, okay? The majority, about 90% of the atmosphere is contained within, 10 miles or so of the surface, but it's three-dimensional. So the energy gained by the atmosphere is not just the energy that comes in and is received, taken in. Not all energy entering the top of the atmosphere is gained. Some is reflected, some passes through. But the energy taken in and used to heat up the atmosphere equals the energy lost. And that's not just energy coming in from the sun above, right? But it's also energy being released by the Earth's surface, okay? And what you'll see is that you add up all the energy taken in equals the energy that's leaving, all right? Finally, energy gained by our surface equals energy lost by the surface. So you have Earth's energy balance, and it applies to three different regions. At the top of the atmosphere, okay, by the atmosphere, which includes from below and above, and then at the surface, okay? And if Earth is taken out of this energy balance, it will try to attain a new energy balance, okay? It will try to attain a new energy balance. Now, the temperature might be different, okay? But if there is an energy, temperature might be different if a new energy balance is attained. But the thing is, if there is an energy balance, the temperature doesn't change, okay? Because the energy entering or the top of the atmosphere is energy equal to energy leaving. Basically, the energy taken in at these different regions is equal to the energy lost. So there's no net heat loss or gain, okay? You can think of energy as heat, right? And what's happening is the Earth is being taken out of energy balance. We're adding greenhouse gases to the atmosphere, which is allowing more energy to be gained by the atmosphere and surface, which is causing then a new energy balance, but at a higher temperature. Okay, we're altering it. Okay, so the Earth wants to re-achieve the energy balance. It likes to stay in balance. It doesn't like to be in imbalance. But the processes, and we look at the next figure, we'll look at the different parts of these, how energy is lost and gained. It changes. Okay, now are you ready to see the Earth's energy budget? Okay. It's a little intimidating at first, okay? When I first saw it years ago in a community college introduction to meteorology class, you know, it was a lot to handle, okay? There's a lot of numbers. You'll see that the Earth and atmosphere energy distribution, okay, how the different parts of the Earth and atmosphere take in energy, lose it. It's very complicated, but it's a very powerful diagram, okay? I really like it because it's going to allow you to see a lot of different things. It's going to allow you to see how the Earth's global albedo is about 30%. It's going to allow you to really see how important the greenhouse effect is, okay? So, brace yourselves, okay? There's a meme, right? Isn't there a meme that says brace yourselves, and then you can, you know, select what you want, and it has that picture of the guy with the hair and the beard, okay? Brace yourselves, okay? So here it is. Are we ready? It's a really cool figure. Okay, now let's start to analyze this figure here, and it's figure 3.38 if you're following along in the book. Hopefully you are following along. Either you're following along as we go, or you're reading first, then going through the lecture, or you're watching the lecture and then reading. Right? Different strokes for different folks. So here's the sun, and here is incoming solar radiation. You see the number 341. So we need to explain what this means. These values are the basically average annual values for energy coming in per area, okay? Energy coming in per area. And so they're averaged over the course of a year, okay? Because the energy per area changes based on the seasons, and it changes over where you are on the Earth, okay? At the poles, the sun is lower in the sky. At the tropics, the sun's higher in the sky on average over the course of a year. And so what is done here is the energy per area is basically balanced over entire Earth's surface over the course of a year. Now, the units are watts per square meter, okay, and you'll hear more about them when we talk about the radiative forcing later in the class, a way to quantify different factors on climate. But for now, you guys, you can just think of them as units, okay? Just think of them as units. So 341 units of energy coming in. And we said per area. Just for now, just think of it as energy, okay? So you have 341 units of incoming solar radiation. And that's composed, of course, of visible near infrared, and ultraviolet. Now, of those 341 units, 78 gets absorbed by the atmosphere. Okay, so 78 of those 341 units of incoming solar radiation gets absorbed by the atmosphere. Okay, and it's used to heat up, okay, the atmosphere. And 79 of those units gets reflected by the atmosphere. Okay, gets reflected by the atmosphere and different parts of the atmosphere, actually, not just the atmospheric gases, but others components of the atmosphere. Okay, for example, aerosols, microscopic solid liquid particles, and clouds. Now, 78 out of 341 is about 23%, and 79 out of 341 is about the same number, the same value percentage, 23%. So 23%, okay, 23% of the incoming solar radiation at the top of the atmosphere gets absorbed by the atmosphere. Another 23% is reflected. So 78 units are absorbed by the atmosphere, okay? 79 units are reflected by the atmosphere. So that leaves what? Well, 78 plus 79 is 157. And if you're thinking in terms of percentage, 23 plus 23 is 46%. So 54%, okay, a little over half of the initial incoming solar radiation is able to pass through the atmosphere. And that's 184 units, okay? And of those 184 units, that 54% that passes through the atmosphere, most of that, the large majority of that, what's left is absorbed by the surface, but not all. You see that 23 of the 341 units, okay, less than 10%, about 7%, is reflected by the surface, okay? So if you take into account not just the solar radiation reflected by the atmospheric gases, clouds, and aerosols, but also reflected by the surface, by the snow, the ice, okay, desert, you get 102 units of total outgoing reflected solar radiation that entered in the top of the atmosphere, but it never was used to actually heat the atmosphere up. And 102 out of 341, do the math, what percentage is that? That's 29.9%, about 30%. Oh! Do we remember that number, 30%? Okay, and what it's think about it for Earth. Earth's blank is 30%. Earth's albedo is 30%, right? What's albedo? The fraction of light reflected by an object or surface. So of the light of the sunlight, which of course is not just visible light, but also near infrared light, if you will, and ultraviolet radiation, well, 30% that comes into Earth's atmosphere is reflected. Okay. Now you also see that most of the radiation that's absorbed, the solar radiation that's absorbed by the atmosphere, is absorbed at the surface. Okay, over twice as much solar radiation absorbed at the surface as by the atmosphere. Okay, and that's what we were saying earlier, right? Most of the solar radiation that's actually absorbed is done so at the surface. Okay, and then you also see, like we had said, most of the solar radiation does pass through, right? More than half does pass through the atmosphere. The atmosphere is fairly transparent to solar radiation, okay? So keep that in mind, especially the greenhouse gases, okay? Now, on the left, we're basically dealing with the fates of solar radiation. On the right side of the figure, you're dealing with the fates of infrared radiation, okay? You're dealing with the fates of infrared radiation shown by these black arrows and the kind of gold highlighting, but there's a couple other energy exchanges going on. There's evapotranspiration shown by this broad blue arrow. Okay, that's referring to basically water evaporating on the surface and then being taken up into the atmosphere. And then there's thermals, basically convection thermals. Remember thermals from earlier in the lecture, okay? So thermals and evapotranspiration are ways to transfer energy in the atmosphere. But they're different from radiation, okay? So What do we see then if we focus on the right side of the figure? In particular, let's focus on radiation, okay? We see 396 units of surface radiation emitted by Earth, okay? That's the terrestrial or long-wave radiation. And then look at this. 356 of those 396 units, basically 90%, okay, of the radiation that's emitted by the surface upward is absorbed by the atmosphere and clouds. And mostly by the atmosphere. Okay, some by clouds, but it's mostly absorbed by the atmosphere. Okay, 90% of the outgoing infrared radiation actually is absorbed in the atmosphere before it leaves space. Okay, can you think of what this is referring to? This is the greenhouse effect, okay, or part of it. This is part of it. You're going to learn the steps of the greenhouse effect. This is part of it. The outgoing infrared radiation is released, and most of it's actually absorbed before it leaves, okay? And when I first saw this, I thought this was pretty incredible, okay? You're telling me that 90% of Earth's outgoing heat, right, for the general person, but now you guys are, learning about radiation. You guys can think of it as infrared radiation. It's actually absorbed by the atmosphere and the clouds, okay? So atmospheric gases, carbon dioxide, water vapor, not nitrogen and oxygen, okay? Those aren't greenhouse gases. Those are not do not interact well with infrared radiation. They let it pass through. Is absorbed by the atmosphere and clouds. Okay. Now, we also have 40 units, okay, so 10% does pass through the atmosphere. The atmospheric window, right? Because remember, radiation emitted between 8 and 11 micrometers generally passes through and leaves to space. We have 169 units of radiation emitted by the atmosphere. So what you've got to remember is that radiation from the surface gets absorbed by the atmosphere, okay, as does some radiation from the sun gets absorbed by the atmosphere, but most of the radiation absorbed by the atmosphere is from the surface. It's upward directed, not downward directed. And then the atmosphere heats up, right? And the molecules move faster, and then they emit their own radiation. And the atmosphere, being at the temperature it is, emits infrared radiation for the most part. Some upward, okay, which then leaves, and some back down. So then notice that you have 333 units of back downward radiation that's absorbed at the surface by atmosphere and clouds. Notice that the surface is able to reflect incoming solar radiation, but it's not able to reflect back radiation from the atmosphere and clouds because this is infrared radiation, okay? And the surface doesn't really reflect infrared radiation for the most part. Now, so what you see is that actually most of the radiation, the downward radiation absorbed at the surface, is actually back radiation from the atmosphere and clouds. Now remember, this is over the course of a year, over the entire Earth, okay? During the daytime, especially at tropical latitudes, at high noon, most of that radiation is going to be incoming, the downward radiation absorbed at the surface is incoming solar radiation, okay? But at nighttime, it's going to be different. There's no sunlight, so the radiation that actually gets absorbed at the surface is what? Back radiation from the atmosphere and clouds. But overall, what you see is over the course of an entire year, okay, over the entire Earth, actually slightly more than twice as much of radiation, twice as much, slightly more than twice as much in downward solar radiation absorbed is actually downward infrared radiation. Okay, hope that makes sense. Okay, hope that makes sense. So remember the Earth's energy balance. Okay, the first part of it, energy entering top of atmosphere equals energy leaving top of atmosphere. Well, how much enters the top of the atmosphere? 341 units. How much leaves the top of the atmosphere? 102 units, that's reflected solar radiation, and 239 units of outgoing long-wave radiation. What's 102 plus 239? Do the math, 341. There's a balance, okay? There's also a balance of the energy gained by the Earth's surface and energy lost by the surface. What I ask you to do is find the energy that is gained by the surface taken in, and then find out how much is lost by the surface, okay? And what you'll see is that they also balance, and then the energy gained by the atmosphere is equal to the energy lost by the atmosphere, okay? Okay, I hope that makes sense. Questions for you, okay? If the amount of clouds were to increase by 10%, correspondingly increasing the albedo, okay? Let's say for some reason there were 10% more clouds in the future, and that caused the albedo to increase, because you might know that clouds can be reflective. They can reflect sunlight, okay? Why, again, it's cooler on a warm, sunny, cloudy day versus a sunny day, okay? Well, if that happened, okay, so there's 10% more clouds and the albedo increases, how would that affect the amount of solar radiation reflected back out to space, okay? Remember that total 102 units of reflected solar radiation by either the surface or the atmosphere or things in it? Would that go increase or decrease? Okay, it would increase, right? We're saying the albedo is increasing, so that should be a big clue, right? There's greater percentage reflected, so those numbers would change, okay? We now have a greater albedo of our planet, okay? And how would that affect the amount of solar radiation absorbed at the surface? Increase or decrease? Let you think about that. If you need to, pause the video. It would decrease, because now you still have 341 units of incoming solar radiation, okay? The sun's not becoming stronger, right? Clouds, in Earth's atmosphere changing in amount, that's not going to affect how strong the sun is 93 million miles away, okay? So the sun's the same amount of solar radiation enters the top of the atmosphere, but what happens? What's different now? More is reflected by the clouds, and less actually makes it through the atmosphere to be absorbed at the surface, so now less than 161 units are absorbed at the surface. Okay, moving on. Let's talk about the greenhouse effect, okay? First, we're going to show a diagram with the greenhouse effect, okay? And I really try to go through how it works and make sure you understand the different processes. Then I have a summary slide with the steps, okay? So first of all, here's a diagram illustrating how it works, okay? So we have long-wave radiation emitted by the surface, okay? And that's also known as infrared radiation. And most of that outgoing long-wave radiation, okay, is absorbed in the atmosphere, right? 90% of the outgoing long-wave radiation is absorbed in the atmosphere, and mostly by greenhouse gases. Okay, greenhouse gases absorb most of it. Clouds do absorb a small portion, but most of the outgoing infrared radiation that is absorbed by the greenhouse gases. Carbon dioxide, methane, nitrous oxide, water vapor, and so on. Now, not all outgoing long-wave radiation gets absorbed by the atmosphere. Some does pass through and escape to space. The atmospheric window, folks. Okay. Now, greenhouse gases then emit long-wave radiation, both up and down, okay? So the greenhouse gases are heated up. They're absorbing the radiation from the surface, along with some incoming solar radiation, but we're not focusing on that in this slide as much. And so they're going to emit radiation long wave in all directions, okay? Not just upward and downward, but also sideways. But this figure is kind of two-dimensional. It's just focusing on, well, it's kind of like a cross-section, okay? Yeah, it's kind of like a cross-section. Two-dimensional isn't the right term, okay? We're not really looking horizontal, we're looking up and down, okay? So up, down, and then what happens? Well, the downward radiation gets absorbed at the surface, okay? So some atmospheric radiation escapes to space, but some atmospheric radiation is absorbed at the surface, okay? So the Earth absorbs the downward directed radiation emitted by the greenhouse gases, okay? Now, here is a summary of the steps, and there are 5 simple steps, okay? And here they are, okay? It's important to know these, okay? It's very important for your understanding in this class, to understand the class that you understand the greenhouse effect, okay? We'll be talking about it more, but it's really important now that you get it down, okay? Understand the steps, okay? So here's the sequence of steps, okay? 1, solar, which we know is shortwave radiation, is absorbed by Earth's surface, okay? That's the first step. Without the sun, basically the Earth wouldn't emit any radiation, and the greenhouse gases wouldn't be able to really do their thing, because in order for Earth to actually have a temperature above absolute zero and emit radiation upward, which can then be absorbed by the greenhouse gases, it's got to have a source of energy, and the sun is the initial source of energy, right? So the solar radiation is absorbed. Then what happens? Earth's surface heats up, and Earth emits infrared, which we know now is long-wave radiation. Okay, infrared radiation has at longer wavelengths than short-wave radiation. Okay, so the Earth emits its long-wave radiation. Now, greenhouse gases absorb most of Earth's outgoing long-wave radiation. Okay, so before it gets to space, before it leaves the top of the atmosphere, most of it's actually absorbed by the greenhouse gases. Okay. And you see why they are so important, because even though greenhouse gases make up a small percentage, actually a small fraction of 1%, not including water vapor, which is highly variable, can make up anywhere from 0 to 5% of the atmosphere by volume. Greenhouse gases, the anthropogenic ones, not the natural one, make up a small percentage of the atmosphere, and yet they're important because with them, the majority of Earth's outgoing radiation gets absorbed. If we didn't have them, this wouldn't happen, folks. Okay, nitrogen, oxygen, argon do not absorb Earth's outgoing radiation well. Okay? And without the greenhouse effect, recall from the earlier lecture, too, that Earth's average surface temperature would be a chilling minus 18 Celsius or 0 degrees Fahrenheit. Okay? Then greenhouse gases emit infrared radiation in all directions, up, down, sideways, okay? And what happens that's important for us humans at the surface is that Earth absorbs the downward directed infrared radiation, and the result of all this is a warmer surface temperature, okay? Warmer than in the absence of a greenhouse effect, okay? Makes sense? Hopefully. Now, let's have a thought experiment, okay? We are moving through this lecture, and the plan for the rest of the lecture is to have the thought experiment for you involving the greenhouse effect, and then we're going to look at a few more figures trying to illustrate how it works, and talk more about a little more about the greenhouse gases, okay? So that's the plan, okay? Now, energy balance. Okay, let's assume that Earth's surface is in thermodynamic equilibrium, right? You want to impress your friends, instead of saying heat balance, say thermodynamic equilibrium, okay? Sounds nerdy, right? So what that means is that the upward radiation emitted by the surface, shown by this green arrow, is equal to the downward radiation absorbed by the surface, okay? Here's the surface. Notice that these two arrows have the same length, okay? Why? Because they're equal lengths. That means the outgoing radiation, which is infrared, is equal to the downward radiation absorbed at the surface. Okay. So the upward radiation is long-wave infrared, but the downward can include not only downward infrared radiation from the atmosphere, but also the solar radiation, right? Remember, the surface absorbs both types. Then, in this case, the average surface temperature is 15 or Celsius, 59 degrees Fahrenheit. That's now, okay? Now let's suppose we do a little experiment to see what happens, okay? Let's say we suddenly remove all greenhouse gases, okay? All of them, carbon dioxide, methane, water vapor, and there's no more greenhouse gases. What would happen, okay? What would happen? In particular, what would happen to the downward directed radiation, okay? Well, if the greenhouse gases were removed, that would decrease the downward directed radiation, right? Because now there's no more greenhouse gases, So there's not these greenhouse gases to emit radiation back down, okay? There's not these greenhouse gases to emit infrared radiation back down, okay? And so what would happen is that now the upward emitted radiation from the surface is greater than the downward energy absorbed by the surface. We do not have an energy balance anymore, no more thermodynamic equilibrium at the surface. And I have a question for you. What happens to the average surface temperature at the surface? Does it go up or down, and why? Think about that. Okay, if you're still listening and haven't paused the video and haven't thought about it, then, pause the video, right? Think about it. Come up with if the surface temperature will go up or down and why. So average surface temperature starts to decrease, go down, okay? Why? Because now more energy is leaving the surface than entering. We have a net heat loss, and that would cause temperature at the surface to decrease. Now what happens then? As the surface cools, radiation emitted by the surface upward decreases until a balance is restored. Why? Well, the surface is cooling, so we know by the Stefan-Boltzmann law that the cooler the surface, right, the less radiation emitted. Radiation emitted by a surface is proportional to the fourth power of temperature. So since the surface is cooling now, the green arrow becomes shorter, okay, less outgoing radiation from the surface. And eventually the downward radiation is now going to be balanced by the upward radiation, okay? At this point, cooling stops because now we have a balance. We have a thermodynamic equilibrium. But the temperature is colder now. What is the temperature? Minus 18 Celsius. 0 degrees Fahrenheit. And this really might make sense to you if you've been following along because that's what we said. The temperature of the Earth's surface would be in the absence of a greenhouse effect. We said that earlier, and here we're saying it again. Okay, to reiterate, right? And sometimes, it's important to reiterate and what we've already said because as you develop more understanding, of these concepts and steps, you start to understand when we say these things. You start to understand why more, okay? And also sometimes you just need to be reminded, you need to hear it over again for it to really sink into your brain, all right? Now, greenhouse gases play an important role in shaping climate. If there's more greenhouse gases, okay, the climate will be warmer. And if there's less greenhouse gases, the climate will be cooler. Okay, more greenhouse gases means more of Earth's outgoing radiation is going to be absorbed, trapped, and the greenhouse gases will heat up more and then emit their own radiation in all directions, some back down, so the surface now absorbs more radiation. If there's greenhouse gases removed, okay, there's less in the atmosphere. Now less of Earth's outgoing infrared radiation gets trapped, less gets absorbed by the greenhouse gases, they heat up less, and therefore they are cooler and they emit less radiation in all directions. And so now the Earth's surface absorbs less downward directed radiation from the greenhouse gases. Okay. Here's a simple figure showing what happens without a greenhouse effect. It's very simple, but it's powerful. Here's the sun. Sun looks big. We have incoming solar energy, okay, absorbed at the surface, and we have outgoing infrared energy. IR just means infrared. Notice that the infrared radiation is at a longer wavelength, greater crest-to-crest distance than the solar radiation or shortwave radiation, right? And the temperature would remain minus 18 degrees Celsius, 0 degrees Fahrenheit in this scenario. And the vegetation is pretty barren, right? Not much can grow in such a cold annual average temperature. But now with the greenhouse effect, it's different. Now, some, and we know most, of that outgoing infrared radiation gets absorbed, okay? And this isn't showing the radiation emitted back down, but you know it's happening, right? And our temperature of the planet is a comfortable 59 degrees Fahrenheit, but what's not comfortable is that it's rising, okay? And now we see a nice green, right? This is a beautiful diagram, right? We go from this light brown color of the surface to this vegetable or vegetational Is that a word, green? Okay. Let's talk about the greenhouse gases more. Okay. And now we're going to look at a lot of information again on a figure. This time we're going to be looking at the properties of the major anthropogenic or human-induced greenhouse gases. And we're going to be learning about which ones are most abundant, and we're going to be learning about how long they last in the atmosphere, and also how good or how strong of greenhouse gases they are, right? Greenhouse effect is good by itself, but what's not good is that it's becoming too enhanced, leading to global warming. Okay. Here is the figure, and it's actually in the book, it's called a table, but I like to think of it as a figure anyway. Table 3.1 in your book, okay? Properties of the major anthropogenic greenhouse gases, okay? Listed in order of abundance. See how you're going from concentration in parts per billion from large to small, okay? So the most abundant anthropogenic greenhouse gas in the atmosphere is carbon dioxide, okay? That's the one with the greatest concentration. And it has an average concentration of 380,000 parts per billion, which if you do the conversion, a part per billion is 1,000 parts per million. So 380,000 parts per billion is 380 parts per million. And the book, you got to remember, it was published in 2010, okay? It's a really good book, although it is a little older. And some of the data in there is outdated, okay? So back then, CO2 concentration was 380 parts per million, but we know nowadays it's near 400, now exceeding 400 parts per million. Remember what we said, say goodbye to below 400 parts per million carbon dioxide concentrations, okay? Okay? All right. Now, we have in this column lifetime in years, okay? Lifetime or mean average residence. Mean is average residence time in Earth's atmosphere, okay? And if you haven't already noticed, the chemical formula for the gas is shown here, okay, and the name, the nomenclature is shown here. Okay, now lifetime in years. CO2 lasts in the atmosphere on average 120 years. We know that, okay. The oldest people ever to live have lived to, 125 or so, okay. I think the oldest person ever was a woman, and she lived to 126 or 127. That is based on actual concrete evidence, okay? Maybe people have lived longer before, right? But based on firm evidence, okay? 120 years. Of course, some CO2 molecules will last longer, some shorter. And CO2 has, let's give it a warming potential of 1, okay? Now, this warming potential is a really powerful, powerful factor, because it enables you to see how strong a greenhouse gas is relative to carbon dioxide. Okay, so just going down to list 1, the next one, gas, is methane, and it's that listed there because it's the second most abundant. Its concentration is now near 2 parts per million, or 2,000 parts per billion. Now, it has a warming potential of 25. What that means is that a single molecule of methane has the 25 times the warming potential of a single molecule of carbon dioxide. Okay? In other words, if this helps you think about it, if this helps you understand it, 1 molecule of methane is equivalent to having 25 molecules of carbon dioxide in the atmosphere. Okay? It's 25 times as strong of a greenhouse gas on a molecular basis. But CO2, carbon dioxide, is still a more important and stronger greenhouse gas overall. Why? Well, for a couple reasons listed in the other columns here. 1, CO2 lasts in the atmosphere 10 times as long. So even though methane is a really powerful greenhouse gas compared to CO2, it only lasts for 1/10 as long. But then, the big primary reason is that there's about 200 times as much carbon dioxide in the atmosphere as methane. So the fact that carbon dioxide is 200 times as abundant as methane and lasts in the atmosphere 10 times as long more than compensates for it being 25 times as warming of a greenhouse gas on a molecular basis. Okay, so there's a lot of factors that go into how the net effect of a greenhouse gas, how strong it is overall, right? And you have to look at these. The third most abundant human-induced greenhouse gas is nitrous oxide. Okay, we'll be talking more about the sources of these greenhouse gases. We talked about them for carbon dioxide already, right? Power generation, transportation, agriculture, deforestation. Methane, we have agricultural sources like cows and sheep, right? Cows moo, sheep baa, okay? We also have landfills, okay? We have natural gas fracking, okay? Turns out natural gas is mostly 70 to 90% methane, so when you dig for natural gas or drill for it, or frack for it, okay, different techniques to get that fossil fuel out of the ground. And when you burn it in a natural gas power plant, it emits methane. Nitrous oxide, by the way, nitrous oxide is known as laughing gas, okay? So it is possible to get high on quantities of it. You don't want to take too much, I think, because too much could be deadly. But you might have heard of this being used during dental surgeries when they need to knock you out and have you go sleepy by for a while. They can give you some natural gas, okay, and do their procedure on you, okay. And there's over 1,000 times as much CO2 in the atmosphere as nitrous oxide. But it lasts nearly the same length, and it's actually a single molecule of nitrous oxide by itself is about 300 times as strong of a greenhouse gas as carbon dioxide, okay? Okay. We have carbon monoxide with a concentration of about, if you do the conversion, that's about 0.13 parts per million. It only lasts in the atmosphere for a few months, okay, a quarter of a year. And it's kind of an exception to the fact that most anthropogenic greenhouse gases last for anywhere from a decade to decades to centuries, okay? And it has a warming potential of 2. But, compared to CO2, but you might know about carbon monoxide being a important factor, an important gas to keep track of in your house. Anyone heard of a carbon monoxide sensor? Maybe you have one in your house, okay? Because if carbon monoxide levels get too high in the home, they can produce health effects. And, by the way, one sad way to commit suicide is to be in your garage, close the doors, and let your car run and let the carbon monoxide come out of your exhaust and into your car, and then you can die, okay? So that's carbon monoxide obviously is a important greenhouse gas when it comes to health. So we're not so much worried about it as a greenhouse effect, but we're more worried about its direct health effect from breathing it in, not so much its ability to warm the planet because compared to the other ones, it's a pretty weak greenhouse gas if you look at its effect overall, because it hardly lasts in the atmosphere very long and it has a low concentration. But we still care about it. Not to say we don't care about it. We want to try to reduce the carbon monoxide emissions. But you might, perhaps on a personal level, I'm saying, be more worried about breathing it in, okay, and its health effect. And that's what you might be more familiar with, but now you know that it can also heat the planet up. CFCs are weak greenhouse gases by themselves. Overall, compared to CO2 net, you'll notice that the CFCs can be several thousands of times as strong as carbon dioxide on a molecule basis, but then what you have to realize is that there's hundreds of thousands or more times as much carbon dioxide as the CFCs, okay, in the atmosphere. By the way, sulfur hexafluoride has a concentration of 0.006 parts per billion. There is 63 million times as much carbon dioxide in our atmosphere as sulfur hexafluoride. And we're thankful for that. We're thankful that sulfur hexafluoride makes up such a small concentration of the atmosphere, because check out its lifetime and warming potential, okay? Sulfur hexafluoride lasts in the atmosphere on average for a staggering 3,200 years. Okay? 3,200 years. So if you do the math, okay, that means there's, what? Sulfur hexafluoride molecules floating around the atmosphere from, what? 1200 BC, okay, or so. Okay, there's sulfur hexafluoride molecules floating around the atmosphere that were present in the atmosphere from when Jesus was walking. Okay, not to get into religion, right? This isn't a class of religion, and respecting all your faiths or your lack of faith, regardless of what you believe about Jesus. Just mentioning that, kind of an interesting point, right? So, yeah, it's pretty interesting, right? There's sulfur hexafluoride molecules present from biblical times, right? Now, also what you see is that a single molecule of sulfur hexafluoride is nearly 23,000 times as strong of a carbon dioxide molecule. Okay, so thank goodness that it makes up such a tiny composition of the atmosphere, because it's such a strong greenhouse effect. Okay, if you had sulfur hexafluoride concentrations, anywhere near CO2 concentrations, okay, even anywhere near nitrous oxide concentrations, okay, you'd really have issues. All right. Review of the greenhouse effect on a diagram scale. Okay, here's a different diagram, okay, but it's I like this diagram a lot because it shows how the greenhouse effect works, and it kind of shows the differences between how the atmosphere interacts with solar radiation and how the greenhouse gases interact with it compared to infrared radiation. So here's the sun. Solar radiation passes through the clear atmosphere. Notice the wording. Solar radiation passes through the clear atmosphere. Okay? So they're saying the atmosphere is clear. Okay, it's pretty transparent to solar radiation. Most radiation is absorbed by the Earth's surface and warms it. That's what we found, okay? Basically, most of the radiation that's absorbed from the sun by Earth is actually done at the surface, not in the atmosphere. Some is reflected by the Earth and atmosphere, 30%, okay? But notice you don't see any greenhouse gases interacting with the solar radiation, shown by these kind of squiggling, in a sense, lines, okay? But what you do see is greenhouse gases interacting with the infrared radiation. So you have infrared, long-wave radiation emitted from Earth's surface upward, and some, in fact, most of the infrared radiation absorbed and is re-emitted by the greenhouse gases in all directions. Okay, so up, okay, sideways, and down. And the effect of this is to warm the surface and the lower atmosphere. Okay. Now, so this is a cartoon of how the greenhouse effect works. Review this, study this and try to understand it, okay? If you have questions, let me know. Now, there's a reason we care so much about carbon dioxide, okay? We've been talking about how it's the most abundant anthropogenic greenhouse gas and it has the greatest effect overall, the net effect that is on climate. And you can kind of start to understand why it's most abundant when you look at global anthropogenic greenhouse gas emissions by gas for 2005. So yes, 2005 is 11 years ago. Okay, some of you were kids, maybe you were in middle school, maybe you were in high school. What you can see is that over 3/4, 77% of all anthropogenic greenhouse gas emissions in 2005, okay, in other words, of all greenhouse gases that were emitted from by human means, okay, were CO2, okay? So you can start to understand why it's the most abundant anthropogenic greenhouse gas, okay? It dominates, and it's dominated for a long time in terms of emissions of greenhouse gases. Methane makes up 15% of anthropogenic greenhouse gas emissions, okay? It's the second most abundant anthropogenic greenhouse gas. Nitrous oxide, laughing gas, makes up 7% of anthropogenic greenhouse gas emissions for the world. As of 2005, the numbers are pretty close today still. And then 1% comes from hydrofluorocarbons, perfluorocarbons, HFCs, perfluorocarbons. These are kind of replacements for CFCs. If you look back, you'll see that CFCs exist in the atmosphere, but what's happened since the Montreal Protocol went into effect in the late 80s is that the CFCs are being phased out at the surface. The production of materials that emit CFCs is being phased out. Okay, so over time we could expect the CFCs to decrease in concentration, and we're not emitting them anymore. Okay, very much, if any, and we're starting to emit more of these HFCs and PFCs, which are kind of similar in the ability to be used as, say, refrigerants and used to make products that used to emit CFCs, like aerosols and hairsprays and foams and bubbles, but they don't damage the ozone layer. They don't break up the ozone into oxygen, monatomic and diatomic oxygen. And here's our friend sulfur hexafluoride. Okay, we don't know a whole lot about it, by the way. Okay, sometimes I've actually had this question asked before. Well, what emits sulfur hexafluoride, right? Because it lasts for so long in the atmosphere and it's so strong of a greenhouse effect. Well, we don't know that much, okay? You could maybe, for your own benefit, do some independent research, okay? All right.